Okay, for risk assessment and process safety management, yesterday I already upload a few introduction regarding risk assessment and also the process safety management. Have you seen all the video about what is risk assessment and process safety management about? Okay. Thank you. Okay. So, as a recap, okay, you already see what is the interaction between process unit, right? Okay, risk avoidance, risk retention, transfer, and also risk reduction. So, all right. Yesterday video up until parallel and series. Okay, parallel and series interaction. So, okay, this is the last slide from yesterday. The computational for probability, reliability, and also the failure rate. So for today, okay, for the example, we will go through the example of the calculation after we have learned all these PSM, okay, process safety management. Okay, because the question need you to determine the overall failure rate, the unreliability, the reliability, and also the MTBF, okay, mean time between failure. Okay, so you already learned about how to calculate the failure rate and also the MTBF. Okay, so today we will look how you can determine the unreliability and also the reliability for the system. I think reliability also already been covered, okay, by using this equation. Therefore, we will look how to calculate the unreliability. Okay, so we will start with the reveal and unrevealed failures. Okay, start from yesterday's slide. Okay, we will look what is the reveal failures and also the unrevealed failures. Okay, there are two different things or two different types of failures. First is reveal and another one is unrevealed. So for the reveal failures, actually is the obvious failure to the operator. Okay, you actually use immediately know there is a failure. Okay, for instance, there are emergency alarm and also shutdown system. Means instantly when the failure occurred, you know, or as an operator, you know that there is a failure. Okay. However, for unrevealed failures, okay, usually it is unaware situation. Okay, unaware situation where you, when the failures occurred until a certain time, then you realize, oh, there is a failures. Okay. Uh, For example, okay, I can give you one scenario or one situation where the reveal failures can be related to your tires. Okay, car tire. When your tire is out, okay, such as tear out and out of service, okay, you know, oh, my tire is out, I need to change my tire. However, for unrevealed failures, the example is the one, the emergency, okay, the emergency tire inside your boot, okay, you don't realize is there any failures unless you make some regular checking, okay. If not, until a certain period, then you realize, oh, even my emergency tire also is out of service, okay, cannot be used, okay. So there is a situation when you have a revealed failures and also unrevealed failures. Okay, yeah, thank you, Jungkit. Okay, tire punctured, okay, when your tire is punctured, so you know, okay, immediately, oh, it is out of order, okay. But when your emergency tire is punctured, you don't know unless you check it, or unless when it came the times when you need to use that tire, okay. So that's the revealed and also unrevealed failures. Okay, so this is the graph of component cycle for revealed failures, okay. A failure requires a period of time to repair, okay, because you just need, okay, a failure must have some period of time so that it can operate again, okay. So this is a fail and operational, okay, 0 1, okay. So there is a certain time, okay, what we call as a period of operation. So period of operation means when you start your operation until the time before the component or the process fail, okay. So from here until here, okay, this is time. From here until here, this is what we call as a period of operation, okay, tau node, okay. This is tau node. When the components or the process fails until before it is been repaired, this is what we call as a period of downtime, okay, tau r, okay, repair, okay. This is time for repair. So this is tau node for operation, tau r is for repair, okay. So did you remember previous class, mean time before, the mean time before failure, MTBF. So this is MTBF from start of your operation until before your component can operate again, okay. So this is MTBF, okay. Instead of you are using your previous equation, MTBF equal to 1 over mu, all right. Now you have MTBF equal to tau node plus tau r, okay. So your MTBF is the period of operation plus your period of downtime, because this is the mean time between failures. So mean time between failures, okay, before another failures occur, okay. So this is MTBF, tau node, and also tau r. Okay, so the revealed failures, okay, for revealed failures, the period of inactivity or downtime, okay, tau r, can be computed by averaging the inactive period, okay, by average. Therefore, we need to make a summation of tau r, then divide the number of n. What is n? N is the number of time the failure or inactivity occurred, okay. How many times the process or the component broken down. So that's the number, okay. So you try to find the average of this inactive or downtime period. So basically from this equation we know for revealed failures you can find the tau r by averaging it, okay. Find the average, okay, of the tau r, okay. You have tau r1, tau two, okay, third time, fourth time, fifth time, sixth time, find the average. That's the tau R for reveal failures. Okay. Then we have the tau naught. So tau naught is also similar to the reveal failures. For tau R, we try to find the average. Okay, so basically for reveal failures, you need to find the tau R and tau naught for average. Okay, try to find the average. If there are only until now, okay, from start the operation until now, the component or the equipment only failed twice. So you need to find what is the tau R and tau naught for both of these situations, then find the average. Okay, so it's up to number of time the failure or inactivity occurred. Okay, so for component we say there's a failure, but for process maybe it is failure or inactivity. Okay, there is no inactivity for the process. Therefore, MTBF is still equal to tau R plus tau naught or equal to 1 over mu. So this is the equation or the formula to calculate the MTBF. You can use 1 over mu or tau R plus tau naught. It depends on your situation and your information. Alright, are you clear? Between the reveal and unrevealed failures and also how to calculate tau R and tau naught. Any question?
Doctor.
Yeah, okay.
This question is not related to the lecture, but about the lecture notes. Some have been asking me about the lecture notes. Can you able to upload it on e-learning?
Okay, question. Let you know I will upload today in e-learning, also in
Telegram.
Telegram. Yeah, Telegram. Okay, okay, I will upload in Telegram after this lecture.
All right, Doctor.
Okay. So basically, okay, this is MTBF. You have tau R and also tau naught. So after you have your reveal failures, unrevealed failures, now there are another terms, availability and also unavailability, A and U. All right. So this is very direct definition. Okay, the availability is the probability the component of the process is functioning. Means if it can be functioning or can in operation, so it is unavailable. It is available. Okay, availability. Unavailability is the probability the component of the process is found not functioning. Okay, remember the question earlier, they are asked about reliability, unreliability. So the question also can ask about the availability and also unavailability. Okay, so don't mix up all these terms. Okay, available and unavailability, A and U. So the equation is availability is equal to mu plus tau naught, because availability is related to the functioning. So you have your tau naught, okay, because this in during operation, and unavailability or U is equal to mu times tau R, where it's related, okay, to the repairing time or during the unavailable, okay, during the broken down duration. Okay, so you have U and also A, just relate the tau R and tau naught. So the quantity tau naught represent the period that the process is in operation. Okay, the earlier definition. But tau R plus tau naught represent the total time. Remember, tau R plus tau naught is equal to what? Tau R plus tau naught. Anyone? Just type in chat. What is tau R plus tau naught? Yes, okay, MTBF. Okay, MTBF 1 over mu. Very good. So, by definition, A is also equal to tau naught plus divide by tau r plus tau naught. Okay, because 1 over mu. Okay, just terbalikkan. Okay, so A and also U is equal to tau r over tau r plus tau naught. So you can also write as A equal to tau naught over MTBF, and U also is equal to tau r over MTBF. All right. So since you are clear, okay.
Doctor, can you admit some of them? They are waiting at the lobby.
All right. Oh, Muni. All right.
Yeah,
Okay.
the guy, memang like that one.
Only 1%. Okay. All right. Okay. So you have A and U. This is the component cycle for unrevealed failures. Okay. Remember, this is for revealed failures. Okay. This is for revealed failures. Okay. But this time it is for unrevealed failures. Okay. For unrevealed failures, there are tau I and tau U. So you have tau naught, tau R, tau U, and also tau I. Okay, so tau I is the inspection interval. Okay, from once the component has been repaired, okay, or it can be in operation until you know or you notice that the component is failed. Okay, this is tau I, inspection interval. Okay, or duration for interval. While tau U, okay, tau U is the average period of unavailability. So actually you need to know what is your tau I first, okay, because once you notice, oh, the component already failed, then you know what's the gap between tau I and tau U. Okay, so this is the average period of unavailability. Okay, tau U. So your unavailability U is equal to half mu tau I. Okay, tau I, the inspection interval. Right, so you got your U. Average period of unavailability is tau U. So once you notice the component is failed, then it will take some time for repairing. Okay, before the component will start back at this point. Okay, at a certain time, after a certain period, then the component is back at here. Okay, so this is start of the component repair. So you start back your tau I. Okay. So before we go for this class example, okay, we look back what is the example from earlier part. Okay, we try to look back because all this question or this example will relate to each other. Okay, the first one. Okay, this is example one. Okay, the water flow to a chemical reactor cooling coil is controlled by system. Okay, by control system. Okay, you know the controller. So as a figure 12.4, okay, this is figure 12.4 about a flow control system. The flow is measured by differential pressure device. Okay, this the differential pressure device. This is DP. Okay, differential pressure device DP. The controller decides on appropriate control strategy, and the control valve manipulates the flow of the coolant. So this is your control valve. Okay, it will manipulate the flow of the coolant. Determine the overall failure rate the unreliability, the reliability, and the MTBF for the system. So you need to find 4 things, okay? Failure rate, unreliability, reliability, and MTBF. Okay, this is the important part. Assume a 1-year period of operation. Okay, because based on the question, sometimes the question need you make a base or assumption such as say 2-year period of operation or 5-year period of operation. So the calculation or the value will change, okay, based on your assumption. Okay, based on your assumption. So you have your controller here, your control valve. This is your flow meter with your DP device and also your pump. Okay, we look how to calculate all these needed. Okay, all the question. Okay, so you have your failure rate data. Usually you can refer, okay, to your textbook for your failure rate data. Okay, it's either in textbooks, in internet. There are lots of reference for failure rate data. So this is failure rate data, okay, for instrument and also faults per year. Okay, because the question also asks over a year, and you have your failure rate data also over a year. Okay, so this failure rate data is based on loss prevention in the process industry books. Okay, so you have your controller is 0.29, control valve, and so on. Okay, so from your figure or your system, you can find what is their failure rate data. Okay, for example, you have your control valve. So you know your control valve have a failure rate data of 0.6 per year. Okay, 0.6 faults per year. Okay. Then you have your controller and flow meter, so that you can refer where is your failure rate data. What is your failure rate data? Indicator lamp, you have a pressure relief valve, pressure switch, solenoid, stepper motor, strip chart recorder, and so on. Okay, so based on your system, you know what is the failure rate data for that particular component. Okay, so these process components are related in series. Okay, because you see all the equipment is related in series. Okay, so this is series system. Okay, series system. So this is one type. Okay, the process component relate in series. Thus, if any one of the component fails, the entire system fail. Okay, because series, yeah, do you remember? Just one fail or one of the component fail, all the system will fail. Okay, it's different from parallel system. Okay, if you have your parallel system, you need all the components fail, okay, for the entire system fails. So the reliability and failure probability are computed, okay, using equation 12.1 and 12.2. Okay, just using this equation, reliability and also failure probability. Okay, so your R and your P is based on this equation. The results are shown here. So you have your control valve, controller, and also your DP cell. Okay, so you have your control valve, controller, and also your DP device. Okay, so what is your control valve? Failure rate, mu. Okay, this is mu. So control valve is 0.6. Okay, what is your controller failure rate, or what is your controller mu? Controller mu 0.29. Okay, control valve, controller, then DP cell. Okay, remember DP cell is the differential pressure device. Okay, so it is belong to pressure measurement. Okay, differential pressure device. So pressure measurement is the mu is 1.41. So you have your mu. When you have your mu, you can calculate your R because you have your time. Okay, based on 1 year. Okay, so 0.55, 0.75, and also 0.24. Okay, once you got your R, your P or your probability is just 1 minus R. Okay, so this for series company or for series system, you need to find your R first before you can have your P. But if you have your parallel system, maybe you can find your probability first. Okay, then you can find the reliability based on your failure rate. Okay. So your reliability, remember, for series, it is summation, not the summation, it is a product of, okay, it's a dot product. Okay, you need to multiply all the reliability. So the reliability for this, for that system, okay, for the system is 0.1. Okay, 0.55 times 0.75 times 0.24. Okay, since the system is in series, okay, even though you have your reliability is quite high for your controller, for your control valve, however, because this system is in series, okay, if only one component is failed, the entire system will fail. Therefore you see the reliability getting low. Okay, getting low because of the system itself. Okay, because the series system. Okay, you need only one component, or one equipment fail, the entire system will fail. Okay, so that's the problem with series system. Okay, 0.1. Any question? Huh.
Ajayan, tutup mic Ajayan.
Dia punya adik sudah kacau. Alright, okay. So you have your R. Then your failure probability is 1 P plus equal to 1 minus R. So 1 minus 0.1, your failure probability is 0.9 because your reliability only 0.1. Okay, your reliability system for over a year is 0.1. So your failure probability is 0.9. Then we look what is the overall failure rate. Okay, what is the overall failure rate? Okay, since from the question, this is failure rate for each component. Okay, remember this is for each component. The failure rate for overall for the system itself is 0.1. Okay, this is R equal to exponential of negative mu. You will try to find what is the failure rate here. What is the mu? Failure rate. So failure rate or mu for the system itself is equal to 2.3 failures per year. What does it mean by this statement? Okay, so the system itself by calculation, okay, state that over a year this system will fail more than twice. Okay, the system will fail more than twice per year. Okay, then the MTBF is computed using 1 over mu, a normal equation. So it is 0.43 year, okay, 0.43 year, okay, not even half year, okay, mean time between failure. So from one failure to the another failure is less than 6 months, okay, just over 0.4 times 12 is 0.4 over year, 0.5 is 6, okay, it's less than 6 months, okay. So from one failure to another failure is around 5 months, then there is another failure, okay. Okay, so the system will rose up every 4 to 5 months. The engineer who designed this, okay, because basically remember this is because the series system, okay, because the series system. If you can change this series system into a parallel system, then you will see how the reliability and also the probability the reliability will increase, okay, and the failure rate will decrease. All right. Then you have your MTBF, overall failure rate. Okay, so the final statement is the system is expected to fail on average once every 0.43 year. Okay, so the maintenance department surely in havoc, okay, for that particular system. All right. Are you clear about the calculation until now? All right, thank you. Okay, so if you are clear, I can include this type of question in your test. All right. Okay, this is another example. Okay, a diagram of a safety system in certain chemical reactor is shown in figure 12.5. This is figure 12.5. Okay, later on we will see. Just look at the question first. This reactor contains high pressure alarm to alert the operator in the events of dangerous reactor pressure. Okay, you have your high pressure alarm. Okay, alarm at pressure more than your pressure of alarm. Okay, once your pressure, okay, your operating pressure is more than your alarm pressure, so the alarm will on. Okay, high pressure alarm to alert the operator. It consists of a pressure switch within the reactor connected connected to alarm light indicator. Okay, alarm light indicator. So in this alarm system, okay, we call it as system A or alarm system 1, okay, whatever you want to call it. It consists another two component. Okay, it consists pressure switch, okay, pressure switch, and also alarm light indicator. Okay, let me help you to highlight. Okay, it's a pressure switch. Then you have your light indicator. For additional safety, an automatic high pressure reactor shutdown system is also installed. Okay, that's your second system. This is your first system, high pressure alarm system. This is your second system, high pressure reactor shutdown system. Okay, shutdown system. You have your shutdown system. The system is activated at pressure somewhat higher than the alarm system and consists of a pressure. Okay, you have your pressure switch also connected to a solenoid valve. Okay, in a reactor feed line. So the automatic system stops the flow of reactant in the event of dangerous pressure. The question asks about compute the overall failure rate, the mu, failure probability P, reliability R, and also MTBF for a high pressure condition. Assume a 1-year period of operation. Also develop an expression for overall failure probability based on the component failure probabilities. Okay, just answer this question first. What is your failure rate, failure probability, reliability, and also MTBF? Okay, can you calculate? Okay, so you need to find mu, P, R, and also MTBF. This is the figure. Okay, this is first system. Okay, now the first system. Okay, this is okay alarm system. Then you have your shutdown system inside the reactor. Okay, so the question asks about mu, R, P, and also MTBF. Can you calculate and give me the answer? Who got first? What is the answer for mu? Okay, I give some information to you. Okay, okay, this is the data. Okay, because remember we have pressure switch here. Okay, okay, we have pressure switch here. This is also a pressure switch. Okay, this. So you have two pressure switch. One is for alarm, another one is for shutdown system. Okay, so you have alarm indicator and also solenoid valve. Based on the table previous table, we can find what is the mu for this particular component. Okay, 0.14 for pressure switch, and you got your alarm indicator 0.044, and also solenoid valve for 0.42. So you have your R, okay, from basic equation, and also you have your P. Okay, now can you proceed to calculate what is your mu, okay, for the whole system, P, R, and also MTBF? Can you try? Or if you don't know how to calculate, okay, you can ask. Okay, never mind wrong or right. Okay, just I want you just try to calculate. Okay, maybe you don't have your calculator beside you. Okay, go take your calculator and so on. Okay, try right now. Okay, you can ask me a question how to calculate, but I want to show you. I want the answer first. Okay, or you can ask me how to calculate. Okay, you can ask me how to calculate, but I will guide you. I don't want to show the answer first. Okay, Junki said that R is 0.48. Okay, you can try. Okay, this is your R and P. Okay, Junki already come with 0.48, P is 0.52, mu is 0.73, MTBF is 1.361. Okay, Yongshi come with, okay, Junki is come up with the answer of R, but Yongshi come with R for system 1, then R for system 2. Okay, which one is right? Okay, never, just, it's up to you. Okay, if you look back, okay, if you can imagine it just like the electrical board or electrical circuit. Remember, if you have your parallel or series, then you have parallel or parallel in series. How to calculate it? Okay, R1 plus R2 is more than 1. Yeah, correct. Okay, it's not possible. You get more than 1. Okay, clue number 1, calculate based on different system first. Alarm system first, and then you have your shutdown system. Okay, because there's a two different system there. Okay, just calculate in series for the first part and then the series for the second part. Okay, second hint is the answer by Yongxi is correct for ARM system. ARM system 1 is correct. Okay, just calculate for the first system first. All right, okay, we look. Okay, so this component, okay, remember alarm system, shutdown system, both systems are in parallel. Okay, but for alarm system, the component is set in series. Okay, this is in series, another one also in series, but this system came up with parallel. How we can define that as a parallel? Okay, remember the statement. Okay, this system is activated at a pressure somewhat higher than the alarm system. Okay, so after the alarm system, then the shutdown system will work. Okay, so it's such as a simultaneously once the high pressure system high pressure alarm system fail, the shutdown system need to operate. But if both are failed, only then the system will fail. Okay, if the high alarm pressure is okay, then there is no failure. But if the high pressure alarm fail but the shutdown system is okay, there is also no failure because the process will shut down. Okay, so no failure. But if the alarm fail and also the shutdown system fail, then your process will have a failure. Okay, there is a failure inside your reactor. Okay, so the hazard will come. Therefore, you need both of the system fail. When you need both of the system fail for the reactor to fail, then it is a parallel system. Alright, so this is R for the alarm system. Okay, this is R for the alarm system. R, P, and mu. Okay, so you have also the MTBF for the alarm system. Then this is for shutdown system. This is your R, P, mu, and also the MTBF. Okay, so Yongxi is right for R1 and R2, 0.84 and also 0.57. Then when the two systems are combined, okay, remember okay, the parallel. So this is you need to multiply all the probabilities for that system. okay, from 0.46 and also 0.165. So your probability is 0.07 and your R is 0.93. Okay, you see got the R system for the total system is 0.93. Okay, yang ni, okay. So it's very high reliability there. Okay, yang ni but this is usually the one that you need to find. Okay, very high reliability. Okay, P, R, and also mu. Okay, negative ln R based on your R. Okay, then finally after you got your mu, you got your MTBF. Okay, for your MTBF is 13.7 year. So the chances for the component or the probability for the component to fail is around after 13 years. Okay, so if you start working after you graduate until you're retired, maybe that system only fail 3 or 4 times. Okay, maybe 3 times only, or two times. Okay, 26 years, 27 years of service, you already reach your age of 55. Okay, it's very high reliability because of the component have been combined in parallel. Okay, because shutdown system and alarm system is in parallel. Okay, if the shutdown system and the alarm system have been connected or have been relate or interact in series, the reliability will go down. Okay, there is a very low of reliability. Once the one of the system fail, that's it. It is a failure. Remember, Junki, this is for your question, because now for the system, the component or that we say for the total system, the alarm system and also the shutdown system is in parallel. That's why we need use this multiply equation. Okay, P1 times P2, or if you have 3, P1 plus times P2 times P3. Remember? Okay. Okay. Previously for the alarm system and also your shutdown system, we use the series of calculation. Okay, series type of calculation because the nature itself in that system. Okay, so you need to think carefully which one is series, which one in parallel interaction. Okay, so this is only relate between two systems. Okay, this one is just the explanation regarding how to calculate the MTBF. All right, so reveal and unreveal. Okay, we go to the second example. Then you try to find what is the availability and unavailability for both the alarm and shutdown system. Okay, remember you already have the mu. Okay, you have your mu, then you can calculate your availability, your A and your U for the both alarm and shutdown system. Okay, so assume a maintenance inspection occurs every once. Okay, occurs once every month, and the repair time is negligible. All right. So this one is already the same statement. Okay. Remember from our previous calculation, okay, alarm system failure rate, okay, yang ni kita dah dapat. This is the one that we already get from our previous example. Okay, this is the calculation from previous example. Okay, 0.18 faults per year. The inspection period is once, okay, once every month. So once every per month, okay. So in a year there are 12, okay, 1/12. It is 0.83 per year. Okay, so what is U? Okay, this formula, okay, you don't see it, okay, because this is for remember this unrevealed failures, okay, U is equal to 1/2 mu tau I, okay. Both systems demonstrate unrevealed failures, remember, okay. So when the statement said this is unrevealed failures, you need to use the equation for unrevealed failures, okay. Okay, so mu is 0.18, inspection is 0.083 per year. The unavailability is computed using this equation. So you got your U and your A. Okay, because for unrevealed failures, you only have one option. Try to calculate your U first. Okay, you need to find your U first before you can calculate your A. Okay, as compared to revealed failures. Okay, for revealed failures, you have two options. You either find your A or your U first. If you got your U, then 1 minus. To find your A, you can have 1 minus U. Okay, but for unrevealed failures, you have no option. You need to find your U first. Okay, then you find your A. So your availability is 0.992. The alarm system is available 99.2% of the time. Means almost all the time the alarm system is ready. Okay, then for your shutdown system, it is U and A 0.977. So the shutdown system is available 97.7% of the time. Okay, so there is a little gap around 0.8% for the alarm system and shutdown system to be in the same time in both failures. Okay, to get both of the system in failures. Okay, so you have your AU and also your A calculation. Okay, sikit lagi for before not end the class. Okay, but to end of this section. Okay, finally you have your probability of coincidence and also MTBC. Okay, previously you have your MTBF, now you have your MTBC. Okay, so sometimes, okay, for alarm and emergency system to be unavailable, it could make or it can mean there is a dangerous process. Okay, that when your system or when your safeguard system, okay, alarms, shutdown system, okay, have been off or unavailable, means there is a dangerous process. Okay, so you can calculate the probability of coincidence where both of the system is off or unavailable. Okay, remember this is a 0.075% for this system to be unavailable, and for the shutdown system is 0.23%, okay, for that alarm system to be available. So you need to find what is the probability for both of the system in unavailable, okay, or in unavailable situation. So that you can calculate through this equation. Okay, you can find the frequency of the episode. Okay, frequency for this incident to occur for both of the alarm system and shutdown system is in unavailable. Okay, so the frequency is equal to PD over TI. Okay, P is the number of the process in time, and the dangerous process episode occurs how many times, okay, in a time interval of TI. Okay, so lambda or frequency is equal to PD over TI. Then you have your mean time between coincidence, MTBC. Before this, you have your mean time between failures. Now you have your mean time between coincidence. Okay, mean time between coincidence is equal to 1 over lambda. If your MTBF is equal to 1 over mu, your MTBC is equal to 1 over lambda, okay, or frequency. Then you can also make it, the equation also can equal to 2 over lambda mu tau I. Okay, this is lambda for this lambda. Okay, this is the frequency of the episode. Okay, but this is the frequency of the PD. Okay, okay, from the previous example, now we try to compute the MTBC. Okay, the MTBC. After you calculate your MTBF, then you need to find the UA, then now is MTBC. Okay, for a reactor of example 12.3, high pressure incident is expected once every 14 months. Okay, high pressure incident is expected once every 14 months. Compute the MTBC for high pressure excursion and a failure in the emergency shutdown device. Assume that the maintenance inspection occurs every month. So the inspection occurs every month, while the failure expected once every 14 months. So this is the frequency, okay, of the process episode. Okay, the failure lambda is equal to 1 failure over 14 months. Okay, once every 14 months. So one episode or one failure per 14 months. Okay, this is just to calculate to convert into a year. Okay, this term is to convert this month to year. So if the question asks about give the statement as a component or the incident of or the incident is occurred once every year, so 1 over 12. Okay, 1 over 12 directly throws 1 over 12 or 1, okay, 1 over 1 okay, for 12 months is 1 over 1 episode per 1 year. So is it 0.857 per year. The unavailability or U can be calculated from tau I. Okay, inspection, remember this is the inspection occurs every month, so 1 over 12. Okay, 1/2 times mu, okay, 0.55 times inspection. Okay, duration times duration for inspection. Okay, 1 over 12. You got your u is 0.023. Okay, this is new equation. Okay, you can relate lambda d with lambda by u. Lambda d over lambda is equal to u. Okay, this is another equation. Lambda d over lambda is equal to u. So you got your lambda d is equal to 0.02. Therefore, your MTBC is 1 over lambda d. Okay, 1 over lambda d. So 1 over lambda d is 1 over 0.02. Your MTBC is 50 year. Okay, your mean time between coincidence is 50 year. So the conclusion is it is expected that a simultaneous high pressure incident and failure of the emergency shutdown device will occur once every 50 year. Okay, once every 50 year. Okay, simultaneous incident and failure of the emergency shutdown device. Okay, if the inspection interval tau I is half, then u equal to 0.03, lambda d 0.01, and resulting MTBC is 100 year. Okay, what does it mean by this statement? Okay, last question before we have some break. Now, what is the conclusion by this statement? If the inspection interval tau I is half, okay, then the resulting MTBC is 100 year. Anyone? Kau ada yang tengah lunch? Maybe one of you or some of you already have your now currently having your lunch. Okay. Okay, thank you, Jungkit. Okay. When the inspection is reduced, your unavailability reduced. Now the inspection is reduced. What does it mean by interval tau I is half? Means your inspection interval is half, means you have maybe twice inspection per month. Okay. Okay, so maybe from one per month you got twice per month, or every fortnight. Okay, every 2 weeks you have your inspection. You can see that's the difference between when you conduct frequent inspection and when you just have a long duration for your inspection. Okay, from 50 year, maybe your plant never have any failures. Okay, 100 year. Okay, 100 year. All right, so from that you can see what's the effect when you have your inspection interval. Okay, what's the effect of inspection interval towards your process. Okay, how your MTBC or how your MTBF and others respond. Okay, how the interaction between the system, parallel system, series system towards your availability, towards your unavailability, towards your reliability, your probability. Okay, there are many tongue twists here. Okay, can help you in order to have your plant in safe condition. All right, so it's 12:24. I think this is end for the first part. Okay, then we have another two parts for this topic. Okay, for this chapter we have a fault tree analysis topic, and then we have event tree analysis topic. Okay, how many of you want to stop here the class? How many of you want to go for another round of FTA vlog? Alright, okay. Saja nak tanya. I just want to ask. Okay, tau I value. Tau I is here. The inspection interval. Okay, from the moment you already repair your component, means why we start from here? Why we start from here? This is when the component repair. Because once you already repaired it, you know it is in good condition. Okay. No, tau 1 is tau I. Okay, tau I is the inspection interval. Is a duration. Okay, the time for your inspection. So once your component is repaired, you know it is in good condition. Okay, maybe macam for example your tire, your car tire, your emergency car tire is in good. You make your inspection. Okay, for maybe in January you make your inspection. Okay, so until certain time, then you remember to make another inspection. Then you already see, oh, the tire also punctured. Okay, so that's the tau I inspection interval from the last time you make your inspection or the last time you already repair. You know, okay, it's in good condition until the time that you finally realize that the component is failed. 1/12 is because the previous statement said that the component is inspected, have been inspected one per month. Yeah. Assume the maintenance inspection. Okay, maintenance inspection is the tau I. Okay, remember the word inspection. Okay, maintenance inspection is tau I, occurs every month. So 1/12. You have one inspection in a month by 12 months. Okay. So if you have your inspection twice a month, so you have 2/12. Okay. 2/12. Okay, so I will get back to you. I will explain later how you determine, how you can define the tau I. Okay, I will explain later how you can define your tau I, where it come from 1/12. Okay, that's some trick here. Okay, it is very tricky to determine the number of inspection. All right, I can end our class today. Okay, here before the fault tree analysis. However, I will post a video regarding fault tree analysis before end of this week. Okay, there are two subtopic: fault tree analysis and also event tree analysis. I want to make sure that you see the video first before we start our class next week. Okay, fault tree analysis and also event tree analysis. Dr. Azam already inform you when is your test? Okay, next week Wednesday. So I will see you on Monday and Tuesday. Okay, so next Monday we will have our tutorial class. Okay, next Monday we will have our tutorial class at 4 p.m. Okay, so I hope that before the class you can see the video regarding this fault tree analysis and also event tree analysis. All right, okay, by then, any question, any other question? Okay, okay, if not, okay, thank you for listening, thank you for your participation. Okay, all right, so your attendance will be taken from your attendance in this Webex. Okay, I will have a list of your participation. Okay, thank you for listening. Okay, have a good day and ready for your test for next week. All right. Okay, thank you.